Hi everyone, today we're going to go through the ImageNet classification with deep convolutional neural networks. So the paper that started the deep learning revolution in 2012. And at the end we're going to implement the AlexNet model in PyTorch. So let's get into it. So in the introduction they give us a bit of background, what was going on in the machine learning community back then. So in 2012 the convolutional neural networks, they weren't like a go-to option in terms of computer vision tasks. So it was mainly because back then they were using a predefined kernels to extract certain features. And it worked well for the dataset like MNIST or CIFAR. And there's a really small output size. But when it comes to bigger datasets, when you have thousands of classes, you need to have something that generalizes well. And as you can see, indeed the shortcomings of small dataset has been widely recognized, but it has only recently become possible to collect labeled dataset with million images. One of these datasets that was collected lately was the ImageNet, and it consisted of over 15 million labeled images in over 22,000 categories, so that was a huge dataset. In order to have something that is robust and generalized well, we need a model with the large learning capacity. One of these models was actually CNN. Basically, we can control the depth and the breadth, and they also make a strong, mostly correct assumption about the nature of the images, so they basically generalize well. But the problem was they were computationally expensive. Back then, no one really used the GPUs to train the networks, and on the other hand, the overfitting with the large networks was a huge issue. So basically that's what they tackle in the AlexNet paper. And one of the reasons that they picked the CNNs is that they have much fewer connection than the fully connected layers. So they're basically easier to train and less computationally expensive. So what they did in this paper, they basically utilized the GPUs to train them, and it wasn't widely adopted by the machine learning community back then. So the GPUs could really speed up the training and push the whole community toward convolutional neural networks. So they built the largest convolutional neural network, one of the largest, and they used an ImageNet dataset from 2010 and 2012 competition. And as you can see, the size of the network made overfitting a significant problem. So they also presented here several techniques that can combat the overfitting. So again, this also push the community towards convolutional neural networks, and that's what actually started the revolution around 2012. So the training took between the 5 and 6 days, and they trained on the 2 GPUs, and all of the experiments suggest that our result can be improved simply by waiting for faster GPUs and bigger dataset to become available. And that's totally true, and that's what happened in the future. So we had much faster GPUs. So I'm going to go briefly through the dataset, and then we're going to go to the architecture. So the dataset contains of 1.2 million training images, 50,000 validation images, and 150,000 testing images. And it's roughly split by 85, 5, and 10%. So they also downsampling the images because they were high resolutions to 256 on 256, and they normalized before putting to the network. So now we go to the architecture. So the architecture contains 8 learned layers, 5 convolution and 3 connected layers. So the funny thing about it is they actually cut in half the whole network because it didn't fit the page. There's actually 2 pipelines that goes there, and one pipeline is for each GPU that they train on. So as you can see, they split the number of the kernels for each GPU. So we got 5 convolutions, 3 fully connected layers, and 3 max pooling. So the interesting thing that they did is basically they reduced the number of the kernel size in each of the layer, actually in the first 3 layers, which is actually not that used these days, and it hasn't been adopted widely. So that's one of the interesting things. The other thing is that they actually, in each layer, they used kernels only from the GPUs that they train on. And in the one layer, so the output of the second one, they actually exchange the feature map. And actually, it wasn't also adopted by the community. But you can imagine how painful it was to write all the libraries for the GPUs from scratch. That was really crazy. But the other thing is they increased the number of feature maps in each of the layer, except the last one. And apparently when they measure it later on, they figured out that that was the bottleneck of the network, that it could actually perform better if they increase the feature map or keep the one from the previous layer. So it's also worth to keep in mind that we also always increase the number of the feature maps in the output layer. So yeah, apart from it, I think we can go into the more of the details of the network. So first of all, they used ReLU. ReLU was not the obvious choice back then, and as you can see on the graph, ReLU solid line reaches 25% training error, 6 times faster than the TAN-H neurons. So the main takeaway from it is that we would not have been able to experiment such a large networks for this work if we had used traditional saturating neuron models. So what does it mean? If you recall, they trained this model for 6 days. If they wouldn't speed up the training process by 6 times, the training would take 36 days. So that significantly speed up the training process. So that was also a huge improvement. And obviously the faster learning has a great influence on the performance of large models trained on large dataset. Totally true. So the next thing is that they train it on multiple GPUs. So basically the network didn't fit into the one GPU, so they had to split it into 2 GPUs. As you can see, the parallelization scheme that we employ essentially puts half of the kernels or neurons on each GPU. The GPU communicate only in a certain layers. It means that, for example, the kernels of layer 3 take input from all kernels map in layer 2. So as I said, it wasn't widely adopted. I heard it's coming back and some of the networks are using it, but apparently this scheme reduced our top 1 and top 5 error rates by 1.7% and 1.2%. So yeah, it was definitely working well for AlexNet. But these days, as you can see, we can feed the whole network at the one GPU easily. So the next thing is the local response normalization. So what it does, it basically it brings forward the neurons that have the highest activation after the ReLU. So it helps to keep the features that matter in the network, and that was actually inspired by the neurons in the brain. So you can see it's inspired by the type of neuron, but the type found in real neurons, creating competition for big activities among neurons, outputs computed by using different kernels. So also that's a thing that hasn't been really adopted deep learning community, but we see the other normalization came up later on, so maybe that was a good kind of starting point to it. But it helped the generalization and reduced the top 1 and top 5 error by 1.5 and 1.2%. So yeah, the next thing that also hasn't been adopted, but it's interesting just to see the overlapping pooling. So what they did is, when you normally have, let's say, a kernel and you extract the maximum values, right? They do not overlap. They just you just take the maximum value out of the maximum value of this kernel and out of this one. But what they did, they basically make them overlap. So it goes like this, and they overlap the next ones. And yeah, it also wasn't adapted. I haven't seen it anywhere else than this, but it reduced the top error, but a small margin, but still it does. And apparently it reduced the overfitting. It's also, I couldn't find any kind of particular proof to it, but yeah. So the overall architecture. So obviously we got the 1000 outputs at the end, and yeah, we get our response normalization layers followed by the first and the second convolutional layer, max pooling, follow both response normalization layers, as well as the fifth convolutional layer. And the ReLU is applied to the output of every convolutional and fully connected layers. So basically we got the whole architecture, and yeah, I'm just gonna go briefly through the overfitting, how they combat it, because I think it's important just to know, because it's basically the main point of this paper. So we're gonna briefly go through it. We're gonna just quickly see the details of learning, and we can go straight into the coding. So reducing overfitting. So our network had 60 million parameters. That's a lot. And back then, obviously, the overfitting was a huge problem. So they presented few techniques that they combated, and one of them was data augmentation that we still use. So they basically randomly cropped the 256 on 256 image to 224 and 224. And also, they actually made a mistake. It should be 227 on 227, because if you put all the values from the architecture, they actually don't calculate with 224 and 224. So the network won't work on these images. It should be 227. So yeah, they randomly crop the images and they horizontally flip them. And that increased the number of the images in the training set by a factor of 2048. So without this scheme, our network suffered from substantial overfitting, which would have forced us to use much smaller networks. So yeah, that's the one thing that was really helpful. The other thing, they change brightness and contrast of the images, and that's a color jittering. But they used PCA and some other more complex techniques, which actually weren't adopted much. We don't use it anymore, but still it was like a good starting point that we later on push forward. So again, this scheme reduced the top error rate by over 1%. So yeah, it worked pretty well. And they also introduced dropout. So that's a recently discovered technique. And what it does is basically force to learn more robust features that are useful in conjunction with many different random subsets of the other neurons. So they dropped half of the neurons in the fully connected layers. Yeah, they used the dropout in the first two fully connected layers, and without dropout, our network exhibits substantial overfitting. Yeah, details of learning. So they used stochastic gradient descent. They used a batch size of 2008 examples, momentum 0.9, and weight decay of 0.005. So the important things, they initialized weights in each layer from a zero mean Gaussian distribution with standard deviation 0.01, and that's what we're gonna do in our implementation also. And they initialized the neuron biases in the second, fourth, and fifth convolutional layers, as well in the fully connected hidden layers with the constant one. So this method accelerates the early stages of learning by providing the ReLUs with positive inputs. So just a quick look at the results. They basically beat the results by around 10%, which is a lot. And these days, most of the networks are battling over 1% or something. So yeah, I guess with all that information, we can move to the coding. So first, we define the class AlexNet, and we pass a module. We got the init function, and we pass the input channels and the classes at the output. So the class is going to be 1000, so we can predefine them. And input channel is going to be free because we're going to use the RGB images. So first we need to define super init, and yeah, obviously So we can start to define our layers in the network. So first layer is convolution. In the first layer we got the in channels equal to in channels. So we got 3 channels, and the output. So we're gonna train it on one GPU instead of splitting it into the 2 pipelines as it was on a architecture in the paper. So we multiplied the feature maps that we had by 2. So it's gonna be 96. And kernel size was 11, stride 4, and panning 0. We can actually copy it and define all our convolution here. Right, I'm gonna define all the max pooling and like non-weights layers later on, and yeah, I'm gonna explain you later why we actually do it this way. So the in channels is 96, out channels is 256. We got the 5 kernels. We got stride 1 and padding 2. So convolutional 3 is 256, 384, and we got the kernel size 3, stride 1, padding 1, and we pretty much keep it for the next 3 layers, pretty much the same. And in the last one we got the in channels to 384, but the out channels 256. And the kernel size 3, stride 1, padding 1. So stride 1 and padding 1 keep the input volume. So we keep the same volume size throughout all these 3 layers. So yeah, then we got the fully connected layer, first one. And the input's gonna be 6 times 6 times 256, because the output of the 5th convolution is gonna go through max pooling, and it's gonna be reduced to 6 on 6, and it's gonna be 256 feature maps, so we just multiply it, and the output's gonna be 4096. So yeah, now we're gonna go to the last layer, which has 4096 inputs, and we output 1000 classes. That's basically it. And we need a norm layer, so it was local response norm, and we set the size to 5, and we need max pooling. So yeah, so kernel size is 3, so we do it overlapping pooling. And the last one is ReLU. So, and that's it. That's basically all the parameters, all the layers we need to define. Now we just need to push forward the input image. So first we do the convolution, then the ReLU, then normalization, and then max pooling. And I'm gonna pull it all, and I'm gonna put it all in the one line. So ReLU and self.conv c1 from x. It's pretty much the same for the second layer. Then the third one is a bit different. We don't have a max pooling, we just have ReLU and convolution. So we can copy it. And we get the last one, which also is followed by the max pooling layer. So then we need to flatten the output. So it's going to be, so now we just pass it through ReLU and fully connected layers. We obviously don't use the ReLU in the last layer. Alright, so that's basically it. But the one thing we're going to do is also initialize the weight. So we need to create a separate function. So we need to create a separate function where we're going to iterate over each layer and initialize it. So let me just quickly show you why we actually implement, why we actually define all the layers in that order. So I'm just going to do print self.modules, and what it means is basically how you actually going to see it. The modules contains all the layers from the network. So yeah, almost. There you go. So yeah, as you can see, now it's so much easier to reference the layers as we define them in a network, in a paper. So for example, if they say in a second layer we get the bias equal to 1, so obviously if you iterate over them, it's so much easier to reference them than if you have all of that mixed together. So that's basically it. And what we're gonna do here is we're gonna iterate over each layer in self modules. As you recall, we got the bias in a second, fourth, so second, fourth, and fifth, and all the fully connected layers. Right. So that's where we got the bias equal to 1. And so we also need to add enumerate. So you get the index also, and yeah. So if layer is conv2d or layer is linear, yeah, so if the layer is convolution or linear, then we if I in bias, then the layer, then we initialize it with the bias equal to 1. So if so you pass the layer and the value is 1, and also each of the layer we initialize from the Gaussian distribution. So normal, so it's obviously normal distribution, so mean was 0 and STD was 1. And now if I is not in a bias, then we initialize it with the 0. And yeah, I think that's basically it. We will obviously gonna test it on random value, so 32, 3, 227, 227, and we'll see if it works. So yeah, we get the output and the shape is 32 on 1000. That's what we wanted. So yeah, that's the whole implementation. That's the whole paper walkthrough. I hope you like it. And if you like it and enjoy it, just please leave a like and subscribe and hit the subscribe button. And yeah, see you in the next one.